Hello everyone, my name is Omar Ben Dali and I work within the research group of Professor Kupnik at TU Darmstadt. In this work, we present a 3D printed ferroelectret which can be used as a force sensor. So first, let's answer the question, what are ferroelectrets? The ferroelectrets, also known as piezoelectrets, are non-polar polymers that exhibit strong piezoelectric properties after treatment. The non-ferroelectrets can be roughly divided into three classes. The first one, as you can see here, is ferroelectrets with statistically distributed air-filled voids. In this class, cellular polypropylene features outstanding quasi-static D33 coefficient up to 300 picocoulomb per Newton. The next class is ferroelectrets with an open pore structure or statistically distributed fibers. And this class is based exclusively on expanded PTFE and exhibits remarkable piezoelectric D33 coefficient up to 1,600 picocoulomb per Newton. The next class, however, is even more promising. This one is based on thermoformed films, for example, EVP, with well-defined air-filled voids. Here, depending on the geometry of the voids, piezoelectric coefficients up to 4,000 picocoulomb per Newton were achieved. However, as the actual state of the environment requires, new materials are needed that comply with eco-friendliness. So in this work, we follow the most recent development of ferroelectrets, which is here the third class. However, using biodegradable material, which is polyactidized, and a new manufacturing route, which is 3D printing. The ferroelectret consists of two identical parts. Each part is a circle with ridges on the top, which are at a distance of 10 millimeters from each other. The first step is the electrical charging. For this purpose, we use the Corona triode with 9 kilovolt for the positively charged samples or -9 for the negatively charged ones. The grid voltage was fixed at 1.5 kilovolt to control the surface electrate potentials. So we get two parts which are charged with opposite polarization, which can be considered as electrets charged with different polarities. Afterwards, the two charged parts are glued together such that the ridges in the two parts are at 90-degree angles to form an artificial ferroelectret. When measuring the mechanical properties of the ferroelectrets, we found out that using the ridges also reduces the Young's modulus of the structure and make it more flexible, and thus large deformation for a relatively small stress can be reached, as you can see here. And furthermore, until a strain of 6% is reached, the ferroelectret sensor shows a linear behavior. However, the piezoelectric response of the ferroelectret is not linear, which should be taken into consideration when designing a sensor. When the forces increase from 0 to 0.5 Newton, a piezoelectric response of approximately 600 picocoulomb per Newton is recorded. And this response, however, decreases with each force step to attain the minimum value of approximately 120 picocoulomb per Newton, starting from 2.5 Newton. This value is then maintained for the rest of the steps. So, thank you for your attention, and I would like to open the stage for questions.